people. I hope we're doing well today. As we discussed in class, the whole purpose of reviewing parametrics is less about, the minute details of how to perform this and that with respect to parametrics, but more just to refamiliarize ourselves with their general contours and their logic and their processes and everything like that, such that when we start applying calculus to it, things don't seem so foreign to us. Okay. In this video and the ones that follow it, we're going to do a whole lot of graphing and a whole lot of eliminating the parameter and a whole lot of other stuff as well. And I'm trying to get a variety of these problems such that we are more and more familiar with parametrics in general rather than simply a particular subvariety thereof. Now, let's go ahead and start with a training wheels question. We have this one. It is x is equal to 2t plus 1 and y is equal to t plus 2. Now, if we want to figure out what the graph looks like, it shouldn't come as a surprise that this is going to be linear, okay? And when we look at some of this, when we plug in -6 into x, we're going to get -12 plus 1, or -11. We plug in -5 in for t into the x of t right here, and we're going to get -10 plus 1, or -9. Plug in -4, we're going to get -8 plus 1, or -7. And the thing is that you can see the fact that they're getting 2 larger for each value of t. Well, that should make sense from the form of it right there. So predictably, we can just kind of do this number. Now, of course, some of those aren't going to be on this -10 to 10 and -10 to 10 Cartesian plane, but let's go ahead and look at y. We plug -4 into here, plus 2. So it's going to get 1 larger each time, and it's going to be 2 larger than its input. So this, of course, is -4, -3, -2, -1, 0, 1, 2, 3, 4, 5, 6, 7, and 8. Well, that's grand, okay? I don't have to worry about these ordered pairs because they're not on the Cartesian plane, but the rest of them can actually be graphed. Now, remember that t doesn't belong on the Cartesian plane. Really, these are our ordered pairs. So we go -9, -3, -7, -2, -5, -1, -3, 0, -1, 1, 1, 2, 3, 3, 5, 4, 7, 5, 9, 6, and lo and behold, it looks exactly like the linear we expected it to be. Now, we can, of course, eliminate the parameter, and in this one, it's relatively simple. We're just going to take x is equal to 2t plus 1. We're going to go ahead and solve for t, and we're going to get t is equal to 1/2 x minus 1/2. Now, the reason that we do that is because y is equal to t plus 2, and if this right here is t, I can take it and, of course, just dump it in right there. And it's a simple substitution, and I get y is equal to 1/2 x minus 1/2 plus 2, because that was our t. And that, of course, gives me 1/2 x plus 3/2, which, if I look at it, that is exactly what that line looks like. Okay. Now, remember that the great thing about parametric is not the fact that it makes graphing a linear more complicated by giving you 2 equations rather than 1. That would, of course, if it just did that, that would be a step backwards, not a step forwards, right? The genius about parametrics it allows us to talk about points on the line, or in other cases, points on the curve, at particular values of t, which, of course, can relate to time if this is a scenario of particle movement or whatever. Now, time t is equal to 0 is at 1, 2. So this right here is t is equal to 0. This right here is t is equal to 1. This right here is t is equal to 2. This right here is t is equal to 3. This right here is t is equal to 4, right? And that's the magic of it. The magic of it is the fact that we can tailor them such that the point on the curve that we're talking about occurs at a specific time t. Okay, let's get to ones that are just a little bit more complicated than this. Now, this one is x is equal to e to the t, and y is equal to t. So we're going to pause real quick and think, what should this look like? Well, if you're thinking exponential, you would be right if it were x is equal to t and y is equal to e to the t. Right, then you would eliminate the parameter and you would simply plug in x for t and it would be y is equal to e to the x. The unfortunate thing here, not unfortunate, but a little more work, is that we need to take x is equal to e to the t and change it into t is equal to natural log x. Okay, in which case if you have y is equal to t, that's the easiest substitution in the world. Y is equal to natural log x. And that is what we get when we start plugging in values. When you plug in 0 in for e to the t, you get e to the 0 or 1. At 1, you get e. At 2, you get e squared. At 3, you get e cubed. Well, e cubed is close to 20, certainly not on the Cartesian plane. And they're just going to get bigger from here, so I'm not really interested in those values down here, right? Not that they don't exist, they're just not going to be on the Cartesian plane, so let's not worry about them. This, of course, is going to be 1 over e, and this is going to be 1 over e squared, and on and on and on and on and on, 1 over e cubed. So remember, this is 1/20th, roughly, for an x-coordinate. Now, for a y-coordinate, of course, it's just the t value. Okay, and so at 1/20th on x, you are at -3 right here, right? And at 1 over e squared, which is, e squared is just north of 7, close to 7.5. And so it's, between 1/7 and 1/8, so it's, right about there. And then 1 over e is close to 1/3, so that's at -1. And then we have 1, 0 right here. And then we have e, which is 2.7, 1828, but roughly 2.7 here on the graph, and it's 1. And then e squared is about 7.5, and so it's right here at 2. And we can see the logarithmic curve emerge just from plugging in the values, okay? Alrighty, well that's easy enough. Let's go ahead and get on to some conics. And we'll t-chart these as well. Of course, we're going to be using different t values. Notice I've populated the t column with unit circle angle values. And now, let's go ahead and plug in 0. Let's look at just the x for a little while. So I'm going to plug in 0 for t, and you're going to get cosine of 0, which is 1, times 4, which is 4. Now, the rest of these are going to be over 2, right? So cosine of pi over 6 is √3 over 2, but √3 over 2 times 4 is 2 √3. And this is going to be 2 √2, and this is going to be 2. And then you're going to get to pi over 2, and you're going to get 0, right? Because cosine of pi over 2 is 0. Doesn't matter the fact that it's multiplied by 4. Now, when you get to cosine of 2 pi over 3, it's going to have the same magnitude as cosine of pi over 3, 1/2, but it's going to be negative, right? Remember that cosine measures the x, the horizontal displacement on the unit circle, and 2 pi over 3 is in the second quadrant, so negative x values. And so these are going to recur. This is going to basically repeat in reverse order these values, but they're all going to be negative. All right, well, let's go ahead and let's do the y values for 0 to pi. I'm going to plug in 0 into sine, get sine of 0, that's 0. Plug in pi over 6, well, sine of pi over 6 is 1/2, times 3 is 3/2. And of course, all of these outputs are going to be over 2 as well, so we're just going to take 3/2 times √2 and 3/2 times √3, And then, of course, that's going to be 3 times sine of pi over 2, which is going to be 3. Now remember, here you're getting into the second quadrant, but here sine is still positive because it's in the second quadrant. So we have, again, those values. They're going to be repeating in reverse order, but they're again going to be positive. Okay. Now, we can deal with these as approximations, okay? So let's go ahead and let's plot. Remember that once we start plotting, we need to ignore the t because these are our ordered pairs. So 4, 0, and then 2 root 3 is about 3.5. So about 3.5 and then about 1.5. Okay, well 2 root 2 is root 2 is 1.4 times 2 is about 2.8. But 3/2 of root 2 is going to be about 2.1. So you get 2.8 and 2.1. So 2.8 horizontally, 2.1. So it kind of sits right there in that little corner of that box. And then you get 2. And then 3/2 of 1.732. Now 1.732 is just shy of 1.8, and if you were to basically take 3/2 of 1.8, you get 2.7. And the difference between the actual value and that approximation are negligible when we're getting into a box that small. And then, of course, you have 0, 3. Now, these ordered pairs have the same values, magnitudes of values at least. They just have different signs, right? S-I-G-N, sign. And so they are going to look like that. And then what you'll find out is if you keep plugging in values from pi to 2 pi over 3, you're going to get these. And so at t is equal to 0, it starts here, and then it sweeps around. Actually, my hand stayed a lot steadier than I thought it would. There you go. And that is the ellipse. And you can check it, of course, by eliminating the parameter. We know that cosine of t is going to be x over 4. We know that sine of t is going to be y over 3. And then if I use sine squared plus cosine squared is equal to 1, I'm going to have x squared over 16, y squared over 9, and the sum of those is going to be equal to 1. Now, in class, one of you asked about, well, what if you swap sine and cosine? And I was going to come back to that question, but I answered something else and didn't come back to it. But let's go ahead and answer it now. Okay, all we've done in this one is it's the same parametric equations except for the sine and the cosine have swapped, see? Okay, so let's go ahead and let's figure out these values. And I won't keep you in suspense. I mean, basically at t is equal to 0, sine of t is 0, right? And so you're going to get 2, and 2 root 2, and 2 root 3, and 4, and 2 root 3, and 2 root 2, and 2, and 0. And you can go ahead and check my work if you want. And you get 3/2 root 3, and you get 3/2 root 2, and you get 3/2, and you get 0, and you get negative 3/2 negative 3/2, and then negative 3/2 root 2, and negative 3/2 root 3, and then 3. Well, let's go ahead and plot those points. Again, remembering to ignore the t value. So 0, 3. Okay. 2, and then this is going to be 1.5 of root 3. Remember, that was about 2.7. And then this is going to be about 2.8 and 2.1. And so that's going to be right about there. And then this one is going to be 2 root 3 and 3/2, and then 4. Those points are looking awfully familiar. And as I go around, what's going to happen is I'm going to plot exactly the same points as I would have if it had been the old one, 4 cosine t and 3 sine t. The only difference is this one starts up top, and its direction is in the clockwise direction rather than the counterclockwise. Okay, so this one goes around like that, and it has a different starting point. It starts here. This is your t is equal to 0. And the thing is that this should make sense to us just if we think in terms of eliminating the parameter. Because if we eliminate the parameter, I'm going to get sine t is equal to x over 4. Cosine t is equal to y over 3. Well, since sine squared plus cosine squared is equal to 1, and since addition is commutative, basically it's a difference between x squared over 16 plus y squared over 9 and y squared over 9 plus x squared over 16, which, as we know, because addition is commutative, doesn't matter in the actual shape of the graph. It only matters for when we're at a particular value on the ellipse, and in what direction the movement goes in as t increases around from 0 to 2 pi. Now I have another question, and this is we've basically used sine squared plus cosine squared in order to eliminate the parameter thus far. My question is, can I eliminate the parameter using inverse trig? Okay, well, let's see. I know that what I was given, okay, and I don't really care which one it is. We'll do the second one. So it's x is equal to 4 sine of t, and y is equal to 3 cosine of t. Okay, if I'm going to plug in here and I need to solve for t, then I know that x over 4 is equal to sine t, or t is equal to arc sine of x over 4. Okay, so we started off with this, and we want to ask ourselves, is it possible to eliminate the parameter doing inverse trig? Well, obviously we need to construct our triangle that is implied by this sine relationship that we just used. Okay, so if this right here is t, and the sine ratio is x over 4, then this adjacent side right here is 16 minus x squared. And if we're going to take y is equal to 3 of cosine t, I want to take this expression for t and, of course, just drop it right in there. And that makes y is equal to 3 cosine of arc sine of x over 4. Now, of course, this right here is simply another way of saying t, right? Because it refers to this angle. Okay, well, what is the cosine of that angle? Well, the cosine of that angle is going to be this radical over 4. So I get y is equal to 3, and I get the square root of 16 minus x squared over 4. And you're thinking to yourself, that doesn't look like an ellipse. Okay, well, let's just fiddle with it a little bit. Let's change the form. And we get 16 minus x squared. Well, if we're going to see whether we can actually put this into the form of an equation that resembles like the standard form of an ellipse equation, I need to get rid of the radical. And so we'll get y squared over 9 is equal to 16 minus x squared over 16. We can, of course, separate these fractions over here, and that becomes 1 minus x squared over 16. And oh my gosh, will you look at that? Okay, so it's not that you can't do it by inverse trig. It's that if you know the Pythagorean identity of sine squared and cosine plus cosine squared is equal to 1, why would you ever want to? But I did want to show you that it actually is possible to do it that way, just, for kicks. All right, well, let's actually try to go the other way. I mean, we basically have seen how we can eliminate the parameter for an ellipse and take it from parametric over to rectangular. But let's go ahead and go from rectangular back to parametric. Okay, well, all we have to do is figure out a way to represent each of these terms as something squared. And that's not all that complicated, right? Because the denominators are indeed perfect squares, and we don't have to do much to basically use our rules of exponents to basically figure that as 2 squared, figure that as 3 squared, and then use our rule of exponents that says a over b to the m is a to the m over b to the m. Now, of course, we're used to using it in this direction, but it's just as true in that direction, right? It works both ways. And so from here, and remember, since sine squared plus cosine squared is equal to 1, since that identity is addition, and addition is commutative, whichever one you want to designate as sine and whichever one you want to designate as cosine doesn't really matter. I would go ahead and just do, sine of t is equal to y plus 1 over 2. Cosine of t is equal to x minus 2 over 3. But I could have just as easily done it the other way. And like I said, it doesn't matter for the shape of the curve. It only matters for when the curve is plotting a particular point, meaning at what t value is it plotting a particular point. And then it also has to do with the directionality of those plottings as t increases from 0 to 2 pi. But if you don't care, then it doesn't matter which one you plug in. So this becomes y is equal to 2 sine t minus 1, and this one becomes x is equal to 3 cosine t plus 2, and basically you have parametricized the Cartesian equation. Okay. In the next one, we'll move on to a hyperbola, but that's it for this first video. As always, if you have any questions, please do shoot me an email. Bye.